Full details of the fetch and execute cycle using these diagrams and explaining these diagrams. First of all, the fetch and execute cycle is fetch, decode, execute, store. But the thing is, sometimes what you're fetching is actually an address. So this is the more straightforward way to understand it. If what you're fetching is data, you fetch or you get the data from the RAM. You decode what the data is. Is it instruction or is it actual numbers or letters? You execute, and then you store the partial result, or eventually you store the permanent result. But when what you've fetched is actually an address, you fetch the address basically, and then you go to that address and fetch the data. So what you fetch, you look at it, it's a reference. From decoding, you realize that. So you go back to that address in RAM that was just fetched, and you fetch the data that's there. Then you decode, and you'll know that this is data rather than an address. So you execute, and you'll see what that means with reference to data later on. And again, either store a partial result in the CPU itself or store the final result back in RAM. The registers that will be talked about down here in the diagram are the accumulator register, which basically stores the temporary result of multi-step process. The instruction register holds the instruction, and the memory address holds the basically data. And the program counter register just keeps track of where you are in the series of instructions. So 1, 2, 3, 4 registers that we will be looking at in the diagram. And I'm just going to read through this. You can skip this part if you want. So here's an example in 3 steps of what happens in these various registers as we add 2 plus 3. First of all, I think it makes sense to take a look at the steps as they would be seen by the processor, in assembler code in fact. The first one is load X. Right, so we're loading the 2. Then the second thing that's going to happen is we add Y. And there are some imperfections in my diagram, and this one, you know, to be similar, would be add 3. And then store. So back up here, 2 plus 3 equals whatever. It's load this, load those 2, and send back the result. So step 1. The loading of the 2, the loading of X. CPU needs to fetch this, basically. So it fetches using the memory bus, or the address bus. It's going to fetch what is at a certain memory address. At that certain memory address, AAA111, in this case, is another address. And that address is from here down to here. It will be 1, 2, 3, 4 letters, LOAD, and rather than a primitive, we're actually using a variable here, so another memory address. So what is at AAA111 is this, which is this. And we have to go one step further because what we're actually loading is what resides at the X variable. The X variable F89789 contains the number, in the context of numbers, 2. And that is the 2 character in ASCII. So capital LOAD and 2 will be then sent back using the data bus. If we look at the various registers at this point, as we get this step going, the accumulator register doesn't have anything. Nothing has been accumulated yet. The instruction is load. The memory address register contains, in fact, 2. Not the address, but 2. And the program counter register starts at where it is. It's going to go this, and then this, and then this, and then this, right? So these are the different addresses that contain different instructions. And we're just doing the first one, and so the program counter is there. Once all this stuff is over into the CPU, the instruction is decoded, it is executed, which is just loading the 2, and stored. The partial result is stored. So in the accumulator, you have stored accumulator register has 2. The instruction register now is finished with that, so it goes back to null. The memory address goes back to null and register, and the program counter goes one more. So AAA111 goes to AAA112. And that's the end of step 1. We have loaded X, we've loaded 2. Now we're going to add Y. The program counter register is located here, so we see what's here, and what's here is an address. And at that address is another instruction and another variable. So we're fetching what's at the next memory address, and what it is this. A, D, D, and ASCII letter 3. So that is what is brought back to the CPU by the data bus. Result is we start this step is accumulators 2. Now we're bringing in add as the instruction, 3 as the operand to add to it, and the program counter is still, at least at this point, still there. So with these registers in those states having fetched, in this step 2 we decode. Okay, I know what to do. We execute. Well, that requires 2 operands. It's not a load something, it's an add 2 things together, and what will be added will be this, and what it will be added to will be the accumulator register. So that's executed. Stored in the accumulator will be the result. So the accumulator register will now be 5. Instruction register goes back to null, memory address register goes back to null, and program counter ticks up 1 to the next, which is that. So we have accomplished adding Y to what was already in the accumulator. And The final step of this simple addition is stow, assembler code in a lot of assembler code languages for store. So again, using where we're at in terms of the program counter, AAA113, that's where we are. We fetch, we send the request, and using the address bus, using the memory bus, we fetch what's there, and what's there is what's there at that memory address, and what is there is simply STO and nothing else. So that is sent back along with a free place in RAM that can hold an int. And we just randomly pick something that's available, 32 bits, and it's this, F89789. So those two things for stow, in the case of stow, get sent back. Started with accumulator register having 5 in it. Now we've got the instruction to store. Where are we going to store? Here, in the memory address register. So in the memory address register now is actually not a value, it's an address, showing you that addresses can travel on the data bus as data, as it were. And our program counter is, I think this is where there's a little mistake. This should, at the beginning of this, it should be AAA113, and then it ticks up by the end of the step to be AAA114. So anyway, when these 4 things are filled through the fetch, decode, okay, know what to do, execute, I take this and I put it there, back in RAM, and I store it in the accumulator. No, not this time. We're just back to null because we're finished. But what does happen is, and I'm saying here not shown, is that the execution in this case is sending stuff back using the data bus to that memory address. And the only other thing to mention here is how the program counter, of course, will go tick up to 1 more, ready for the next line of instruction.